I'm Jake O'Neill, creator of Animographs, and this is how a helicopter works. I chose a design that's seen decades of consistent service in roles like search and rescue, life flight or medevac, law enforcement, military, commercial, and private civilian ownership. This is the Bell Helicopters Model 407. As usual, I've taken liberties for the sake of teaching that may deviate from this specific model. Let's have a general look around the aircraft before diving into specifics for each system. The very basic principle of rotorcraft is the spinning wing or blade that generates lift without requiring forward movement, versus fixed-wing aircraft or standard airplane design. The incredible rotational forces, or torque, generated by the main rotor and blades are countered by the tail rotor, also called the anti-torque rotor. Working together, these devices allow predictable, controlled flight in varying conditions. A special kind of engine, called a turboshaft, powers the aircraft. It shares some similarity to jet engines in airplanes, but also differs in key ways we'll see later. It's anchored to the roof, just behind the main rotor. There are multiple fuel tanks beneath that, secured in the passenger or cargo area. Towards the front, there's the cockpit, with controls for the pilot and the optional dual pilot package. Large windows maximize visibility, not only to the front and sides, but also above and below the aircraft. There's a wire strike protection system, with wire cutters above and below the body. It weighs around 2,700 pounds empty. For comparison, the average small SUV weighs about 3,000 to 3,500 pounds. It can carry 2,300 plus pounds added weight, including all crew, passengers, cargo, and fuel. When flying at the lighter side of its weight limits in normal temperature and weather conditions, it has a 20,000-foot flight ceiling, a max cruise speed of 135 miles per hour, and a range of 400 miles. In normal working conditions, a max range flight might be around 125 knots for 3 hours with 20 to 30 minutes of reserve fuel. The engine is rated to continuously produce 650 plus horsepower. With a general idea of its characteristics and capability, let's get into the details, starting with the airframe. The frame is made of aluminum and aluminum composite materials, as are the outer panels or skin. Some panels have an internal honeycomb structure for lightness and strength. The tail boom is made of aluminum and is designed to flex some. Attached to the tail boom, there's a horizontal stabilizer to help keep the helicopter nose steady and avoid excessive pitching up or down in flight. The vertical fin also helps take some of the load off of the tail rotor to keep the craft flying straight and resist main rotor torque. The airframe and skin is lightweight but strong enough to support both the engine and the main rotor with associated components, which take up the entire area above passenger, crew, and cargo areas. Let's have a look at the engine. This helicopter features a single turboshaft engine. Many helicopters are twin-engine models. Instead of a single unit, there are two identical turboshaft engines which share the workload. The turboshaft engine gets its name because it's designed to power a mechanical shaft, instead of producing thrust with a stream of jet exhaust. The combustion chamber is located at the back of the engine. This is the heart of power production. Compressed air is piped in at the sides. Some air surrounds and cools the combustion liner. The primary inlet at the back swirls air as it enters the chamber for better mixing. A fuel injector nozzle at the center sprays fuel into the stream. There's an igniter plug, not unlike a car spark plug, positioned in the path of the fuel-air mixture. The engine starter at the gearbox gets everything rotating. The starter also works as the electric generator when the aircraft is running. It has its own cooling air intake in the side of the cowling. Air and fuel mix while the engine spins up. The igniter plug ignites the mixture. Once burning, the process will continue on its own as long as air and fuel are supplied. The heat and pressure from expanding combustion gases now passes to the turbine section to drive various turbine wheels. Turbines have many blades to efficiently take power from combustion gas. Between these turbine wheels, there are rows of stationary blades called stators to guide gases straight through the passage instead of just twisting with the turbines. Turbine sections are split between two separate key engine functions. The first two turbine stages are connected to a shaft which drives the forward air intake process. This is called the gas producer turbine. The remaining two turbine stages connect to a hollow shaft that wraps around the compressor shaft and extends into the engine gearbox, eventually powering the main rotor. This is the power turbine. It can also be called a free turbine since it has no physical connection to the gas producer. The exhaust gas flow turns 90 degrees as it enters the exhaust chamber, having spent its energy. Exhaust is guided out the top and towards the back through a curved pipe. At the front of the engine, we see the compressor section. Drawing in and compressing air makes for more powerful combustion. The compressor rotor, powered by turbines, draws air in as it squeezes into the increasingly narrow channel before sending the now compressed flow through pipes at either side to the combustion section. There are air intakes on both sides shaped into the external cowling. There's a screen in the intake chamber to catch debris. Helicopters operating in snowy or dusty environments may have other devices here to keep foreign particles out of the incoming airflow. Now that we've seen the engine's core, let's follow the transmission of power out of the engine. A couple connected gears greatly reduce RPM. If the power turbine spins at 48,000 RPM, the output shaft is rotating at about 6,000 RPM. the power output gear is splined to the main drive shaft. Let's zoom out a little and get a better look. While this drive shaft does have many smaller components and segments, it's important to note that the main rotor and tail rotor are inseparably connected and always rotate together. That said, in the case of critical engine problems or failure, the rotors need to be able to freely rotate on their own, disconnected from the engine. This is called autorotation. Pilots practice autorotation maneuvers to safely land a helicopter with no engine power at all. During autorotation, the pilot angles the craft towards the ground so that the force of air in the dive keeps the rotor spinning, ideally with some forward movement. At about 35 feet above the ground, the pilot will flare the craft backwards, using the rotor's built-up spinning energy to create an air cushion between the craft and the ground. At the right height, the cushion has dramatically slowed descent for a safe landing, just as rotor spin or inertia and lift is depleted. Now, let's zoom back to the engine and drive shaft connection. To seamlessly disconnect engine power from the drive shaft, there's a special component here called the freewheeling unit. The outer shaft is splined to the engine power output gear. There's an inner shaft which forms part of the main drive shaft. These outer and inner components aren't directly connected. The magic happens between them with a one-way clutch assembly called a Sprague clutch. A ring of individual metal wedges called sprags are held in a circular retainer with a spring. As the engine delivers power to the outer shaft, the friction presses against the sprag's surface, causing it to tilt. Its oblong shape makes it get taller as it stands up, gradually forcing the opposite curved face into contact with the inner shaft surface. As force increases from the engine, sprags wedge even tighter into the space, further securing the connection. However, if the drive shaft has more power than the engine, or if the engine fails completely, the drive shaft pushes the sprags and they rotate out of connection. It only works one way. It's also automatic and always functional, so the drive shaft can rotate on its own if it needs to. Now, let's follow the drive shaft forward towards the main rotor. There's a rotor brake assembly here that works like a car disc brake. A lever in the cockpit lets the pilot apply this brake to slow the rotors quickly after landing. It's only used on the ground after engine shutdown. Moving forward, there's a special section of drive shaft here with spring-like structures at each end that allow greater flex or minor misalignments between the engine and transmission. This also keeps sensitive parts in the engine and transmission from imparting harmful vibrations to each other. This is where the drive shaft connects to the transmission. Power travels through a set of bevel gears, reducing input RPM or rotation speed. A hollow shaft connects to a planetary gear set above. Planetary gears allow further RPM reduction, but are also very strong while keeping a small form factor. The bevel gear drives the central sun gear. Power flows from the sun gear to smaller planetary gears, which are mounted in a planetary carrier. This is where the main rotor mast connects to the system. The mast extends from the bottom of the transmission upwards all the way to the top of the rotor assembly. Splines at the planetary carrier drive the mast. If the drive shaft entering the transmission is spinning at 6,300 RPM, these gear sets have reduced rotation to around 400 RPM at the rotor. The transmission is mounted with a 5-degree forward tilt, so the cabin sits level during forward flight, and a 1-degree left tilt to compensate for translating tendency, which is a helicopter's natural tendency to drift right from slight tail rotor thrust effects as it works to keep the aircraft from spinning. Mounts are made from rubber-like materials designed to absorb vibration. There are springs at each side that extend from mounting pylons to the transmission case for the same reason. Having seen the transmission and main rotor mast, let's trace power backwards from the engine. With a zoomed out view, you can see that the drive shaft is not entirely straight, but is divided into sections between components and along the tail boom to the tail rotor. Let's have a look at these segments. Just behind the engine gearbox and freewheeling unit, we have the forward short shaft. There's a special flexible connector here between these parts. It's a stack of discs designed to deform together. Shaft sections are bolted to the disc stack in a perpendicular arrangement so they can tilt slightly, independent of one another, but still rotate together. Tracing the drive shaft towards the rear, there's a flywheel to add rotational mass to the system. And behind that, the oil cooler unit. It's driven by the main drive shaft and powers a blower fan to cool engine and transmission oil. There are bearing hangers with bearings mounted before and after the unit, upon which the rotating drive shaft rides. The drive shaft then passes beneath the engine oil tank. This section is called the aft short shaft. As we reach the tail boom, there's another flexible coupling disc pack and bearing hanger. There are 4 more sections like this along the tail boom. The boom is designed to deflect or bend some under normal operating forces. As we reach the tail rotor gearbox, the drive shaft connects to another set of bevel gears, which reduce rotation speed from about 6,300 to 2,500 RPM. As power flows to the tail rotor output shaft. And there you have it, the engine and drive components for the helicopter from front to back. Naturally, there are many supporting components and systems, like engine and transmission oil, filters, pumps, electrical systems, and so on. Fuel is also part of the propulsion system. There are 2 tanks, with the forward tank mounted beneath passenger seats, and the aft tank mounted behind, for a total fuel capacity of around 130 gallons. Now that we've seen how the helicopter is powered, let's focus on the rotors and see how that power is used to generate lift. This is the main rotor in all its glory. The mechanical movements you're seeing come from pilot controls in the cockpit. These movements affect all possible flight directions: forward, back, left, right, up, and down. The main rotor mast, which we saw previously, never tilts or moves off its axis, as it imparts rotation force to the rotor hub assembly and blades. Let's clear away all other parts for a moment, leaving just the blades. The helicopter is sitting on the ground, ready for takeoff. The blades themselves are airfoils with a profile similar to an airplane wing. Though there are more complex sub-forces at play, in very general terms, all we have to do is rotate all of these blades at once to generate lift and upward movement. This is called collective pitch, where all blades change the same amount of pitch together. Here at the blade tip, you can see it looks just like an airplane wing tilting for takeoff. It's doing essentially the same thing. Now that we're floating in the air, let's fly forwards. If the spinning blades form an imaginary disc, we want to tip that disc so it generates more lift at the back to push the helicopter forward. To achieve this, each blade is allowed to tilt on its own axis. Again, the rotor mast drives the blades to spin, but never leans off its own fixed vertical position. To make this next part very clear, I'll detach a single blade. As the red arrow shows, this individual blade changes pitch as it makes a full rotation around the rotor. Pitch change causes the blade to naturally tilt itself up and down as it presses against the air. This is called flapping, and that's literally what the blade is doing. It's hard to see it all at once, as the blades together still look like a flat tilted plate. But if I freeze that one blade in place at the rotor, you can see the flapping motion is really dramatic. It moves up and down a lot. This is what's actually happening. We'll see the parts that allow blades to move like this in a bit, but the important thing is that this flapping motion happens all on its own, just by changing blade pitch as the rotor pushes it through the air. It's kind of like when you fly your hand into the wind outside a car window. So, if you want to tilt that imaginary disc and fly in a particular direction, you only need to control this flapping cycle. When it's high on one side and low on another, you go in that direction. This is cyclic pitch, or blade feathering. It's worth noting here that collective pitch changes also cause blades to tilt, but they're not flapping up at one side. They're just all tilted together, up or down. This is called coning. For maximum control, cyclic and collective pitch changes can happen at the same time, for example, to gain or lose some altitude while still heading in a particular direction. There are other important forces at work here that affect helicopter design. First, when certain blades angle up or down like this, while others remain relatively level, the more angled blade tends to rotate a little bit faster for just a moment, like pulling your arms in while spinning. To account for this, each blade has a flexible connection to the rotor, and can advance or retreat a little automatically to make up for these minor speed differences across the rotor. When moving in a particular direction, say forward, the advancing blade might generate much more lift than the retreating blade as it pushes harder against the oncoming airflow. Causing unwanted leftward roll that shouldn't be present in straight forward flight. To make up for this dissymmetry of lift, as it's called, we rely once again on natural blade flapping. With forward flight, for example, blades have cyclic input, which means the advancing blade is pitching steadily downwards, while the retreating blade is pitching up. Now, oncoming air naturally presses the advancing blade down even more, so it generates less lift, and the retreating blade up for added lift, automatically balancing lift differences across the rotor. As we saw a moment ago, for forward flight, blades reach max pitch at the left side of the rotor, so they'll hit max upward flap at the back. There's a delay between maximum blade pitch and upward flap. In my research, I found that there's some disagreement here. Many sources attribute this delayed effect to gyroscopic precession, which says if you impart a force on a spinning disc, the effects happen at a 90-degree offset. While gyroscopic forces are certainly at play with rotor dynamics, this is not a rigid disc or a rigid system, and some helicopters are apparently designed to reach max blade pitch at, say, 70 degrees before achieving max flapping angle, which would invalidate that rigid 90-degree gyroscopic law. Seeing these flexible blades as taking some time to respond to airflow around them as they change pitch seems like the more fitting way to describe their behavior. This is called phase lag, as it refers to helicopter rotor function. Before we move on to the physical components that make all this possible, just keep in mind that the flexible blades themselves and their ability to freely shift within multiple degrees of freedom counteracts and adjusts for many complex forces at play with rotor design. Without these constant adjustments, the system would quickly tear itself apart if it could fly at all. With that, let's bring back the rest of the rotor's components. Starting at the top, there's the mast nut, which secures the entire assembly. Beneath that, the upper and lower plates. Sandwiched between these, the yoke, which is splined to the mast. Let's focus in on each component for a single blade. There's the lead lag damper, which is directly attached to the top and bottom plates. It's made of metal and rubberized materials that allow the part to flex. At its center, there's a special rubberized piece called an elastomeric bearing. Rings of flexible material alternating with metal make this a kind of stiff spring. The very root of the blade is anchored here through the blade spindle. The elastomeric bearing flexes, allowing the spindle to shift as needed. This lead lag bearing does just what its name says, managing the blade's forward or backward movement to lead or lag as it rotates around the helicopter. After the spindle, there's the pitch horn, which is the control lever for pitching or feathering the blade. Then the grip, which holds the actual blade itself. A flexible pivot bearing keeps everything in place while allowing pitch changes. The pivot bearing is anchored to the yoke, which surrounds the whole chain of blade components. Most of these parts are made of lightweight metal, such as aluminum, while the yoke is built up from laminated fiberglass layers and is designed to bend. This is how the blade gets its flapping motion. There are stops on top and bottom hub plates to keep blades within operational limits for coning and droop. As for the blade, the outer skin is fiberglass. There's a stainless steel erosion strip at the front. It's got a fiberglass spar at its leading edge for added strength, called a D-spar because of its profile shape. The core is Nomex honeycomb material. Nomex is a proprietary fibrous material that's strong, light, and can withstand lots of heat. The trailing edge is also a fiberglass strip, with a trim tab at its midsection to balance individual blades. The blade droops while resting, but lengthens and becomes strong with centrifugal forces during flight. The blades and their connecting parts form a much more organic system than it first appears. It's flexible yet very strong, self-adjusting to elegantly meet complex flight conditions. Let's follow the chain of components down to see how pitch changes are handled. All of the parts you see here make it possible to enact both collective and cyclic pitch change to the blades while the rotor is spinning in flight. Each blade has a pitch horn, as we saw previously. Pitch link tubes extend downward with spherical bearings at the end that allow some movement. They connect at four sides to the swash plate assembly. This contraption is what translates input from relatively stationary components to rotating parts. You can already see that, as the swash plate tilts, each pitch link gets specific, individual input. The swash plate assembly has two main parts. The lower plate, which doesn't rotate, rides on a large spherical ball called the pivot bearing that allows it to tilt in all directions. It has a hinged bracket or scissor link to stop it from rotating vertically. The lower plate holds large bearings upon which the upper plate smoothly rides, allowing it to spin as it rests on the lower plate. The upper plate also has scissor links. Since engine power flows from the mast through plates above, these scissor links allow the upper swash plate to tilt while transferring that power. Notice again what happens when the swash plate tilts. Pitch links raise and lower in a cycle as the upper swash plate spins upon the tilted assembly. Having seen cyclic input, let's now look at collective controls. Again, collective affects all blades at once. To achieve this, the pivot sleeve and bearing can slide up or down, lifting or lowering the entire assembly. This adds or subtracts pitch from every link at once, no matter which way the swash plate is tilted. So, for example, the pilot can roll left with cyclic input while also gaining altitude by adding some collective input. Though my model is patterned after a specific craft, you'll find most helicopters solve these design requirements in similar, equally elegant ways. As we move away from the rotor, let's trace the flight controls from here down into the cockpit and eventually to the pilot, and see how all this input arrives at the rotor. For swash plate tilt, there are control tubes at either side. The right or starboard side is the longitudinal control tube for input along the front-to-back flight axis. Since parts have various offsets in the system, tilting diagonally here ends up giving blades max pitch at the sides, in keeping with our earlier flapping demonstration. The left is the lateral control tube for input along the side-to-side flight axis. And there's a collective link at the center to move the collective lever. These linkages pass through bell cranks and control tubes to arrive at 3 corresponding servo actuators. Generally speaking, a servo translates commands given to it, and a hydraulic actuator uses hydraulic force to perform work. So, these servo actuators take inputs from pilot controls while adding hydraulic force, since they would otherwise be difficult to move. There are, however, springs extending from actuators to bell crank levers to aid the pilot should these servo actuators lose power during flight. There's a small reservoir for hydraulic fluid. Here's what these components look like in action. As we pan down into the body of the helicopter, we see 3 corresponding control tubes extending from the back of the cockpit up to the servo actuators. They reside in a control tunnel that sits between the cockpit and the passenger or cargo area. Again, control tubes for longitudinal and lateral pitch are at the sides and take their own inputs. The collective tube is at the center. However, collective input doesn't just affect the center tube. Both side tubes are anchored to the center lever, called a mixer lever. Because collective input moves all 3 tubes together for a seamless, additive result. If we pan back up top while collective commands travel through the system, You can see that all 3 actuators and connected tubes move with collective input. This is how the system adds collective and cyclic together. Finally, let's head into the cockpit and see the origins of this control chain. The pilot sits at the right side. The flight stick, or cyclic, is centered in front of the pilot and handles all cyclic input. The collective lever is down at the pilot's left. The collective lever's linkage is pretty straightforward. There's a friction knob nearby to adjust the feel of the lever, so it moves more freely, or maintains its position but is a bit harder to move. We'll get into specific buttons and switches here when we look at the cockpit later. The flight stick or cyclic controls are a little more involved. Left to right movement translates through tubes and levers to the lateral control chain. Forward or back motion moves the large tube underneath, which translates through to the longitudinal control chain. Notice how pure side-to-side motion doesn't affect front-to-back parts, and vice versa. Of course, the system gives freedom to blend these axes at will. Front-to-back controls have some extra components. There's a bracket and levers linked to a cam. As the cam passes through a slot, some left-to-right input is automatically blended into the forward-to-back movement. For this particular model, designers found a tendency for side roll when transitioning to forward flight, and built a correction into the flight controls. Here's one more look at the whole control chain. Cyclic and collective commands pass from the cockpit up to the servo actuators and eventually to the swash plate and blades themselves. Heading back to the cockpit, let's switch to directional control, or in other words, the tail rotor. This is where foot pedals come into play. Again, I've included optional co-pilot controls here. There's a knob at the front to adjust pedal distance for proper pilot foot position. A couple of bell cranks pass pedal movement through the system. Co-pilot controls are hard linked such that both pedal sets always move together. The foot pedal linkage components travel through the same tunnel as other controls, but cross inside the roof structure instead of on top. There's a servo actuator in the body midsection just before the tail boom. A long control tube travels the length of the boom to eventually connect with a series of levers that move a pitch control tube. Now that we're at the tail rotor, let's zoom out some and take in the whole unit so we can make sense of the pitch controls and so on. You'll remember from before the drive shafts and bevel gear set. From the larger bevel gear, a connected output shaft extends out the left side of the helicopter's tail. At the end of this shaft, there's a splined hub that holds tail rotor blades. This is how the tail rotor gets its rotation. The output shaft is hollow, so the pitch control tube can pass through it. Linkages connect this tube to mini pitch horns at each blade. The tube moves back and forth, affecting blade pitch. The whole assembly spins enabling pitch changes while in motion. Each blade is mounted to the hub with spherical bearings. They both tilt the same amount, but at opposing angles. Since the rotor always spins the same way, changing blade angle is how the helicopter alters thrust direction to swing the tail around. There's a little more going on at the hub. Like the main rotor, the tail rotor might experience different conditions at each blade. If moving forward, for example, the advancing blade might generate more thrust as it presses hard against the oncoming airstream, while the retreating blade might generate less. The tail rotor also has its own built-in flapping function. The hub floats on a trunnion, which is a kind of pin that allows parts to pivot. It has elastomeric bearings at each side. This trunnion is splined to the drive shaft. The hub is clocked 45 degrees on the trunnion. So instead of just tilting straight in or out, this has the effect of gradually increasing blade pitch with more hub tilt. It can be a little hard to see the tilting and pitching happening as one movement, but if we fly around to the blade tip, notice how the arrow and blade profile points a little more to the left or right with hub tilt. If we move the foot pedals to pitch the blades, notice how this hub flapping still works to add or subtract pitch. So, if there's more air pressing against the bottom blade than the top, the inequality will cause the hub to tilt, adjusting blade angles accordingly. Now, the bottom cuts a little less into the air, making less thrust, while the top pitches a little more. Pitch links are attached with spherical bearings so the rotor can still flap, even as pitch commands come through. Each blade has counterweights front and back and lengthwise at the hub for smooth operation. And here's the tail rotor in action, keeping the helicopter aligned with dependable directional control. Now that we've seen the inner workings of propulsion and flight control, let's head back over to the cockpit and see what the pilot sees when flying the helicopter. Starting with the dashboard and displays. Newer helicopter models use digital displays for most things. Past versions of this same model had 30+ warning lights along the top and 16 or more round gauges and flight instruments in the main dash area. These screens have a seemingly endless array of panels and options. The current view is what a pilot might have active at times during a flight. Let's look at a few notable instruments here. On the right, or primary flight display, we see radio frequencies at the top, both for navigation and communication. Moving down, we see the attitude indicator, which displays helicopter pitch and roll. The vertical tape-style readout at the left shows airspeed. The right side is the altimeter, which indicates current altitude, with an associated vertical speed indicator that shows the rate of travel up or down. The large compass beneath that is the horizontal situation indicator. It shows the direction of travel towards a predefined point in space, distance remaining, and so on. These are headings or points from a flight plan. The two dials at the left are repeated from the left side display, so let's head over there. This is the multi-function display, intended as a kind of supplement to the primary display. It's currently showing the PSI, or Power Situation Indicator, as the large dial. It indicates available power based on 3 items to the right. Q is engine torque. It's measured by tracking oil flow in the gearbox, since this flow changes as pressure is exerted on engine components. MGT is measured gas temperature. This is the temperature of exhaust gas at the gas-producing turbines. These are the spinning turbines that drive the compressor to suck air into the engine. And NG is the rotation speed of the gas producer turbines. The green range is within normal operating limits. Yellow is the cautionary range. And red means some critical measurement is being exceeded. Gray areas turn red if the needle enters the gray region. The smaller dial to the right is the dual tachometer. The longer needle indicates main rotor rotation speed, with its readout displayed as a percentage under the NR label. The smaller needle indicates power turbine rotation speed, which is the turbines that send power through the engine gearbox out to the main rotor. Down the right side, we have pressure and temperature gauges for the engine and transmission, generator amps and volts, and fuel gauges for total fuel quantity, pressure, and flow rate. The hours reading at the left indicates total engine operational hours, which is tracked for maintenance intervals and other logging requirements. Outside of the displays, there are backup airspeed and altitude instruments, and various switches for critical functions. Down below the main dash, there's an audio unit for controlling internal and external communications, music, internal speakers, and more. Heading to the cyclic control stick, there are spaces for switches based on installed components. Things like communication modes, external cargo hook release, skid float inflation if installed, and so on. Moving left of the pilot's seat, we see the collective lever. Mounted to this lever, there's the engine throttle twist grip. Moving to the control head, there's a switch to start the helicopter's engine, and another switch for toggling different exterior lights. Directly above the collective, there's a couple of panels. The section towards the back is a circuit breaker panel for many critical onboard components. The forward panel controls lighting for the dashboard instruments, other internal and external lights, air conditioning, anti-ice and defog units, battery, and more. There's a lever for the rotor brake nearby to slow rotor rotation after landing and engine shutdown. The main battery is tucked underneath the dashboard and is accessible through a hatch at the front. I didn't realize until researching this project that helicopters entered mainstream usage 3 decades after the first powered airplane flights. The intricacies of spinning wings versus fixed wings took longer to iron out. Such graceful command over hovering, taking off, and landing on a specified point is a sight to behold.